Every massive structure we build, every highway, residential development, and earthen dam relies on the structural integrity of the dirt beneath it. When that earth gives way, the results are catastrophic. Excessive rainfall, seismic activity, or hidden geological weaknesses can trigger rapid collapse, turning stable ground into a violent landslide in seconds. The core dilemma for geotechnical engineers is predicting these failures before they occur, using only a limited set of subsurface data. To solve this, engineers rely on specialized geotechnical analysis software like WESLEA. It functions as a digital laboratory, allowing them to test the limits of the Earth virtually. The ultimate objective of this analysis is to translate the unpredictable physical Earth into a single, definitive mathematical metric that dictates whether a project is safe to build. There is an inherent gap between raw field data, like soil borings and laboratory tests, and the rigorous demands of civil engineering blueprints. WESLEA acts as the bridge in this borehole-to-blueprint workflow. The software takes messy, site-specific geological data and standardizes it into a clean, iterative digital model. We are going to construct a geotechnical model from scratch to reveal exactly how this software evaluates safety. Every calculation in this model is designed to produce one central metric, the factor of safety. In physics, the factor of safety is a simple ratio. It divides the resisting forces, the natural shear strength of the Earth, by the driving forces, which include gravity and any external weight pushing down on the slope. It is the definitive binary decision maker that either greenlights or cancels multi-million-dollar infrastructure projects. We start with a stark 2D coordinate grid. This is the blank spatial canvas where the engineering model is constructed. Engineers first import raw soil investigation reports and borehole data directly into the software interface. Using this raw data, the software maps out the soil stratigraphy, snapping distinct color-coded layers into the grid to form a precise cross-section of the multi-layered slope. But geometry alone cannot predict physical behavior. Engineers must assign precise material properties to these digital shapes based on rigorous laboratory testing. This requires defining critical parameters for each individual layer, such as specific soil density and shear strength. If these parameters are inaccurate, the entire model is compromised. The software processes the data it receives. It cannot correct bad initial assumptions. The physical accuracy of this foundational stratigraphy dictates the validity of every subsequent mathematical calculation the software performs. A static soil model is insufficient. Real-world slopes are subjected to constant environmental and man-made forces. To account for this, engineers apply boundary conditions to simulate the physical constraints of the surrounding landscape. They then apply external loads. These downward force vectors represent heavy construction equipment, vehicular traffic, or new building foundations pressing into the earth. Next comes the most volatile variable in slope stability, groundwater. When water enters the soil matrix, it creates core water pressure. This dashed line represents the water table, and the arrows show the outward force exerted by trapped water, which physically pushes soil particles apart. Seasonal changes, such as heavy rains raising the water table, drastically degrade the slope's internal stability over time by reducing the friction between those particles. Failing to parameterize these invisible environmental dynamics is the leading cause of delayed, catastrophic infrastructure failures. With the physical and environmental parameters locked in, the software must now locate exactly where the slope is most likely to break. It does this by calculating slip surfaces, the theoretical fracture planes where the Earth could shear and slide downward. WESLEA tests two main types of failure models: circular arcs, common in uniform soils, and jagged, non-circular multi-angled lines, which occur along distinct geological weak points. The software iterates through thousands of these potential fracture planes in a matter of seconds, hunting for the exact path of least structural resistance. Along every single line, it compares the driving forces pushing down against the soil's shear strength holding it in place. Out of those thousands of tests, the software isolates the single most critical slip surface, shown here in red, where failure is most imminent. This specific critical fracture plane is where the software calculates the final factor of safety. Through this digital analysis, millions of complex physical interactions are condensed into one actionable number for the engineering team. A factor of safety below 1.0 means the driving forces exceed the resisting forces, and failure is imminent. However, structural standards usually demand a built-in safety buffer, requiring a score of 1.5 or higher. Generating this initial score is where the automated calculation ends and human engineering judgment begins. If the initial factor of safety is too low, engineers use WESLEA to rapidly test alternative design scenarios. This diagram shows two potential mitigations. On the left, reducing the physical angle of the slope, and on the right, embedding a vertical retaining structure. Both solutions push the factor of safety readout safely above 1.5. This ability to test design alternatives back-to-back saves massive amounts of engineering time and mitigates physical risk prior to construction. The final step in the workflow is generating comprehensive, automated calculation reports to document all material assumptions and ensure strict regulatory compliance. WESLEA's iterative loop ensures that structural vulnerabilities are solved in a digital laboratory long before construction crews ever touch the physical earth. The digital parameterization of geology is rapidly evolving beyond these isolated desktop models. Geotechnical software is increasingly being integrated directly into building information modeling, allowing for seamless cross-disciplinary design between civil and structural teams. Furthermore, the use of geographic information systems and remote sensors provides continuous slope monitoring, shifting these models from static calculations to live data streams. This leads directly to the deployment of digital twins, live digital replicas of physical infrastructure that update their factor of safety in real time based on live sensor data. Soon, machine learning algorithms will be trained on these massive datasets to preemptively predict slope failures before the standard safety thresholds are even triggered. These advancements are critical as global infrastructure expands into more challenging geological terrain, demanding highly precise, sustainable design practices. As our infrastructure scales and environmental conditions grow more extreme, rigorous modeling software will remain our primary defense against the unpredictable forces of the Earth.